Exercise 12.2 is really a review of the alkyne addition reactions and from a previous chapter. And these are all going to be one step in this exercise, but what we're building to are exercises where we can use these in multi-step exercises. You could see that the focus of this, sort of the central hub of this web, is an alkyne. Let's start with ways to make that alkyne. You'll notice that there are two. Both of the ways to make the alkyne start out with dihaloalkanes. You have two halogens on each of these starting molecules. In other words, you have two leaving groups. With two leaving groups, you can do two elimination reactions. And each elimination reaction creates a pi bond. So what we can do here is use a strong base. That's what you need to do any elimination reaction, are leaving groups and a strong base. Here we can use excess, and here to make it even more efficient, we use a really strong base, sodium amide, NaNH2. That's the first step. Now, if you just added excess sodium amide to this, there's a hydrogen here. The base would rip that hydrogen off, and you would have a carbon nucleophile there, which wouldn't be that stable. So to stabilize the molecule, as a second step, you do a water wash. And this carbon nucleophile sort of steals a hydrogen from water. And so it becomes stable again. So when you're doing these elimination reactions, you use excess base, sodium amide, NaNH2, and you follow that up with a water wash, so here H2O. And that will give you an alkyne, no matter whether the two leaving groups are on the same carbon. That's called a geminal dihalide, coming from the Latin word for twins, like the zodiac sign Gemini stands for twins, or vicinal, that's if they're on neighboring, if the leaving groups are on neighboring carbons. And that's coming from the Latin word for neighborhood, vicinity, right? Also is another English word with that root. So we can make alkynes by starting with dihaloalkanes, either geminal or vicinal, and using excess sodium amide in one step and a water wash in a second one. These numbers in front of the steps are really important. The ones and the twos, those are really important because if you don't have those there, a person would think that you just mix all this stuff together, and then these reagents would react with each other rather than with your carbon molecule. So it's crucially important that you write those numbers there. Okay, well, let's say we have our alkyne. What can we do with it once we have it? Well, if we look at this going up, and here let me, just so these don't get in our way, if we look at this going up, this reaction here, what we notice is that one pi bond leaves. So we start with 3 bonds total, 1 sigma and 2 pi, and we end up with 2 bonds total, 1 sigma and 1 pi bond. So we lose a pi bond. And both a bromine and a hydrogen are added. This had 1 hydrogen to begin with, this one has 2, so that means we added a hydrogen there. Notice that the hydrogen went to the less substituted carbon. In the original molecule, this carbon on the end is just bonded to 1 carbon, so that's primary, and this carbon in the middle is bonded to 2 carbons, so that is secondary. The hydrogen went to the less substituted carbon. That's Markovnikov addition. And in Markovnikov addition, to add H and Br, all you do is add HBr. You don't have to add peroxides. Adding peroxides would give you the H and the Br, but where the H would add on the more substituted carbon, and the bromine would add on the less. So that's what you'd get if you used peroxides. But if you just want this molecule, which has the H on the less substituted carbon, then you just add HBr. Crucially, you would just add 1 equivalent of HBr. So you wouldn't add excess. Okay. While we're here, how could we turn this HBr into our geminal dihalide? Well, we could just add HBr again. right? If we had HBr again, instead of the 2 hydrogens, we'd have 3, and then another bromine. Notice that it's Markovnikov addition of hydrogen and bromine again. Another hydrogen goes onto the less substituted carbon, another bromine goes onto the more substituted carbon. So if you just treat it with one equivalent, you get this haloalkene. If you treat it with a second equivalent, you get a dihaloalkane. All right. Now, in this next reaction, we're turning the alkyne into a ketone. Now, this involves addition of H and OH. The OH needs to go on the secondary carbon, and the H on the primary carbon. Once you have the OH, it ketoenol tautomerizes into this product. So this is Markovnikov addition of H and OH. This is going to be acid-catalyzed hydration. If you ever start with an alkyne and end up with a double bond to an oxygen on the more substituted carbon, then you know you needed to use water, sulfuric acid, and mercury 2-sulfate, also called mercuric sulfate. Those reagents do an acid-catalyzed hydration on the alkyne. They turn it first. The first thing they would do is to turn it into an enol. Right, it would add an H on the less substituted carbon and an OH on the more substituted carbon, and then this would ketoenol tautomerize, so a hydrogen and electrons would switch places, and you'd end up with your product here. That's acid-catalyzed hydration of an alkyne to get a ketone. The next reaction is similar, but you'll notice what happens here is the OH goes on the less substituted carbon. So here, this was the secondary carbon, and this was the primary carbon that we had. Here, this is the secondary carbon, and this is the primary carbon we had. The OH here goes on the less substituted carbon, and the hydrogen goes on the more substituted carbon. That's anti-Markovnikov addition. And so, if you want to do anti-Markovnikov hydration of an alkyne to get an aldehyde, then you would use hydroboration oxidation. Now, in the first step, you could either use 9-BBN or any dialkyl borane, so R2BH, any of those would work. Once you do that, the second step is the standard H2O2 and NaOH. So that's the recipe for hydroboration oxidation. And that would give you this transformation. Now at first you'd form an enol. It would add an H and an OH, the OH on the less substituted carbon, the H on the more substituted carbon. Right? This is anti-Markovnikov addition of H and OH, but then they would tautomerize. The H would move over, the electrons would move over, and you'd end up having that, which is your product here. So if you ever have a terminal alkyne, an alkyne at the end of a carbon chain, and you turn it into an aldehyde, it must have been hydroboration oxidation. Okay. In this next one is a really crucial reaction because in it we form a new carbon-to-carbon bond. You'll notice that here in our original molecule we have 1, 2, 3 carbons, and here we have 1, 2, 3, 4. So this is a two-step process. The first thing we have to do is to turn the carbon in the terminal alkyne into a nucleophile. We have to turn this into a nucleophile. We can do that by first adding a strong base. Now remember, if you add a strong base, something like sodium amide, NaNH2, that will steal this hydrogen off the end. Right? The base has a full negative charge. It will steal that hydrogen, and the electrons will go onto the carbon there. So by adding sodium amide, you create this carbon nucleophile. So that's the first step. In the second step, you want to look at whatever carbon chain you have that you want to add, and here it's a CH3, and you add a leaving group on it. And what'll happen is your carbon nucleophile will attack that, and the leaving group will leave. And so you'll form a new bond between the alkyne carbon and the carbon in your alkyl halide that you add in the second step. So this two-step procedure is able to create a new carbon-to-carbon bond. First, add sodium amide. That turns this terminal carbon into a nucleophile, and then do an SN2 reaction. Just put a leaving group on whatever carbon chain you want to add. Now once you have that alkyne, that internal alkyne, a triple bond with carbons on both sides, once you have that, you can reduce it. You can add hydrogen. You could either just bubble hydrogen through it, H2 gas with platinum, palladium, or nickel. You wouldn't use all of those, you just use one. That would take it straight to the alkane. That would add as much hydrogen as you want. Or you can turn it into a cis or a trans alkene. To get the cis alkene, you would add hydrogen gas in the presence of Lindlar's catalyst. To get the trans alkene, you would do the dissolving metal reduction, sodium in the presence of ammonia. And there's a video for the mechanism for this in that previous chapter, in the alkyne chapter. Okay, next. What if we want to start with an alkyne and add two bromines trans to each other? So we get a dihaloalkene. Well, the two things we add, two bromines, that's the reagent that we need, Br2. And you'll remember from the alkene chapter that those add anti, and so that's why they're trans on this double bond. Now, it's important that you only use one equivalent if you only want to add two bromines, because if you just add bromine, especially if it's excess, then you'll get this product, and then you'll add another two bromines, and you'll end up with this next product here. So these are just a question of how much bromine did you add. Finally, here we have, notice again how many carbons we have originally. 1, 2, 3. Here we have 1, 2, and the third one is separated from it. This is a really important pattern to notice. If you ever break two carbons apart, completely separate two carbons, like we do here between carbons 2 and 3, if you completely cleave that bond, the only way we know to cleave that bond is with ozonolysis. Now, when you do ozonolysis on an alkyne, you still use ozone, O3, but in your second step, you want to use water. If you do it on an alkene, in the second step, you'll want DMS, dimethyl sulfide. And notice how, if you do ozonolysis on an alkyne, you don't get aldehydes and ketones, which is what you get if you do it on an alkene. Instead, an internal carbon will turn into a carboxylic acid. That's where you have a carbon double bonded to oxygen with an OH on one side. And a terminal carbon will turn into carbon dioxide. So a carbon on the end of an alkyne, if you do ozonolysis, will turn into carbon dioxide. So what we've seen in this exercise is that it is a sort of quick review of all the one-step reactions that we learned in the alkyne chapter. And just looking at this web, you can see all of the possibilities that are open to you, both to make an alkyne and with what you can do once you have made the alkyne. So in this video and the previous one, we've looked at one-step reactions that we know for alkenes and alkynes. We're going to combine that with substitution and elimination reactions for the rest of the chapter, where we'll explore multi-step synthesis.